Yeah, good morning, ladies and gentlemen, and welcome to our talk, What is Spectral Color Data and Why Should a Developer Care? And you see this gemstone here, and this will Alexandrite. I think it's the right pronunciation. Please correct me if I'm wrong. And we will talk about that more in the course of that talk. Originally, I planned about 1 hour, but I've seen right now that we have even 90 minutes, so we can really use the time. So please ask questions if you don't understand something. It's quite interesting for me also to see, to not exactly know the level of the people. So that's why, if it's too complicated, just let me know. If it's too easy, I go quicker. Yeah, I will briefly introduce what is Fogra and what is color, because when we start talking about spectral color, it's very important to talk about what's color basically, and then going from color to spectral imaging, seeing what are the pros and cons of spectral imaging. I will talk about what I think about what this is. And then the main part of that talk is, of course, using the spectral information in PDF files. Yeah, the industry needs independent research, and the main motivation for the foundation of Fogra was in 1951, that small and medium enterprises, as today said, they don't have an independent body who is really giving vendor-neutral information, because if they have an argument with Van Roland or Heidelberg or big vendors, you can guess who's right. And that's why they said, okay, why not putting a little bit money together to found a neutral group down in Munich and do this vendor-neutral research. And Fogra is an abbreviation, acronym stands for Forschung, Research in the Graphic Arts, so that's why the FO and the GRA. It's often talk about who neutral is one. You will talk about neutral experts. But when people say they're independent experts or consultants, I say, okay, if people say they're independent, are there other people saying I'm a dependent consultant? I've never heard about such a dependent consultant. I said the easy question to ask if someone is neutral or not so neutral is, who's your owner? Very easy question, who's your owner? And then you can very easily say how neutral or how not so neutral are the answers of this guy. And for Fogra, it's quite easy. We are lobbyists of the interest of our members. So the members are really constituting the basis of Fogra, and they provide the board of directors who's ruling us. So that's why the members of Fogra, the owners of Fogra are the members. Like if CGS and EFI and Kodak and GMG is a member of Fogra, I think about twice doing it once in favor of one or not in favor of the other one. So that's why it is a very nice constitution, a very nice framework which allows us, or which damns us to neutrality. In the US, I always say I reflect Sarah Palin and Barack Obama at the same time. So I represent the industry quite from Heidelberg and paper manufacturers upstream to print buyers like the Siemens or Nestle or Dr. Spiller Biocosmetic in Munich. So that's why I try to represent those interests. And seeing the contribution of members, we have 750 members right now. 60 of them are national and 40 already international members. And the majority of them are still print shops. So conventional print shops, but more and more digital print shops. And so that's why we see ourselves as a lawyer of the printer to really think or represent their voices and interests. There are similar organizations, of course, like UCRA here in Switzerland, PIRA in the UK, GATF in US or IDO in Spain, but there are a lot of infrastructure which has been changed, funding and so forth. So it is very hard in many countries to get the funding for this vendor-neutral research, and that's why other or comparable organizations have downgraded. Like PIRA is just 5 people and organizing committees. GATF has just closed or merged, so that is a situation where we are very happy in Germany that we have an infrastructure where we can apply for projects still if they comply with strict guidelines. So this is also important to understand how Fogra is financed. We need about 5 million euros a year to survive, and 1 million is about our membership fees, 2 million from research funds from the country, state and other project bodies. And you see already that then we end up with 3, and in order to make no losses in order to survive. In order to get the black zero, we are allowed to make normal profitable business, and this is like certifications, this is selling media wedges, this is making a Fogra symposium or something like this. What we do at Fogra, basically 4 parts. We talk about basic research and development based on that projects spanning over different departments, from pre-press where I work, printing technologies, environmental, chemistry, material, and post-press. We do some research, 1 or 2 year research projects. For pre-press right now we talk about soft proofing, norm line evaluation, device link qualities and this kind of stuff. Then we go make consultancies, measuring opinions, measuring expert opinions based on that knowledge. Dissemination and training, like today, making talks and presentations, symposiums, and last but not least, committee work and standardization. It is, again, we are lobbyists of the interest of our members, and they ask us to make international standards rather than local standards or de facto standards, because, let's say, a print inking maker, print ink maker is interested in having an ISO standard for the compliance of his inks, not a German standard, and a Swiss standard, and an Austrian standard, and a North Bavarian standard. And this is very paid in nowhere in the international or global organization or the global market. So let's come to the topic of our talk. What is color? And basically, when we talk about color, we have always 3 topics or 3 objects in mind. We need a light source. We need an object which is reflecting parts of that light, and of course we need a human observer who is able to digest, who is able to perceive, this kind of stimulus, this kind of physical light entering his eye. And only these 3 elements are constituting the color impression. There's always a direct way that the light from the light source goes directly to the eye. We talk about that also. And at the very beginning, like 100 years ago, smart people found out that color is 3-dimensional. That means all colors can be represented, can be 100% represented by 3 independent variables. Not 2, not 1, not 4, exactly 3. So that means if you make experiments, you can select whatever stimulus you like, whatever spectral stimulus, you pick it, and then if you have 3 independent variables, you can match those kind of colors. That is very important to see that you need at least 3 independent numbers to define a color, and we will talk about it in more detail. And what we always see here already, that colors might change. So since this is the interaction of the light and the object, if you have different lights and you see what's going on here, then the color, the perception is changing. So you see the same sample here, the same physical object looks different when illuminated by different light sources. So this is very important message at the very beginning, because if you talk about color communication and you look about the same piece of print ink on paper here, and your customer looks the same ink on paper under different light, and you call each other and he is complaining, then you already see that you have a big misunderstanding in color communication. And so for the graphic art, we said, okay, what do we need, and what kind of average light is the best one to use as a compromise, as a mean value. And so we agreed to use, what is the average light source for the graphic arts? Everyone heard about D50.
Cigarette light?
Not cigarette light, almost. So D50. Who knows who the D stands for?
Daylight.
Daylight, exactly. So it's not incandescent, not tubes. It is a daylight phase with a color temperature of 5000 Kelvin. So approximately, not so blue like now, but a little bit more warm white. We come about that. And one more, I will always write ISO, so British English color, so I always use the U here, not to confuse you. Okay, so how we can understand color and how can we describe color? And the first thing normally what you learn about color is that color is perception. Color is not a material property. So that is the biggest misconception people have, they think this object is red. And that is unfortunately wrong. This object viewed under this illumination appears red. That is right, because if I switch off the light, it's dark. If you have, and we have more colors, we will show you nice, better effects. So color is a perception, like hearing, like smelling, like taste. So it's interesting to ask, how can I measure perception? How can I measure what someone feels, what someone likes? And that was the first question I had 10 years ago when I entered that field. And we will come to that, how this was, to answer how this was possible by simply learning that color, remembering color, the human body is, or the human visual system is very weak. So if I tell you, just remember this color is red, and everyone goes to this Photoshop and reproduces, and then I put the displays side to side, you can get a bouquet of flowers, but not the same red. Simply why the color memory is quite weak. But on the other hand, if I have two similar samples put aside next to each other, and I ask you, do they match or do they don't match, then 90% of the men and 99% of the women are very consistent in their answer, saying yes, it matches or it doesn't match. So this kind of differential property of the eye, we can see very easy and very critical small slight differences, will be used. And this was used in the experiments from 1931 and before to see what is the discrimination of colors. And so they did experiments in those times and found out that over the wavelengths of colors from the 400 nanometers blue area to the 700 nanometers in the red area, so where in the area where our brain, our rods and cones are sensitive, we have this kind of color matching functions which mimic, which reflect the way how our systems acts or reacts on a stimulus entering our eye. And coming to that, there was some time from 1931 to 1976 where a lot of research was done, and we have seen that colors need to be identified. Not only to say, oh, print this with HKS 14, or Pantone warm red, or RAL 3003. This is a common way people communicate color, but you will see that this is very not very well-defined way of communicating color. 90% of our environment is not taking really care of exact colors. You know, you don't blame if the ribbon is not the same color. You don't care if this is really your CI color. But there are applications, like if you get new teeth and they should look the same next to each other. You are very sensitive, believe me, if there's a color match. If your car gets repainted, you will always think about whether the painter does a good job or not. In heritage, in picture and artwork, and in graphic arts, some instances, the color reproduction is very important, and there it is very important to understand how color works and how can we achieve correct reproduction. And for this, the C-Lab system was introduced to allow for an unambiguous identification definition of color perception. And this was published in 1976, and it has 3 channels, L, A, B. Who have heard about LAB the first time today? So anyone knows LAB? Just from the name, okay. The first channel is the lightness channel. It goes from 0 to 100%, from the very dark to bright. It has 2 color difference channels. They are termed A and B, and they are mostly limited to 8-bit. And so you see this kind of range. Bless you. But it's very important to understand that sometimes if you specify color, that the limitation from going from here to here is computer science limitation. It's not that there are no colors being more negatives than 127, like neon colors or something like that. You have them. They are basically restricted by the way of encoding colors in that 8-bit world, and that is important to know. It is defined for surface colors, so we will see later that mostly we have these 3 objects. We have a light, we have an object, and we perceive them. That is called a surface color. Everything which appears dark when you switch off the light is a surface color. In contrast, we have self-luminous colors like a display, like a candle, a cigarette lighter. And my favorite question is, what is the moon? Self-luminous? Yeah? It's reflected light. But we will come later to something like the misconceptions that people say, yeah, a monitor and a print never can match, this is emissive and this is reflective. No, it's bogus. And with the moon, you see, it's a concept, it's a context. Yeah, if I asked you 500 years ago, you would most likely see it self-luminous because it appears to really shining. But we know from physics or from other sources that it's just reflecting the light from the sun. So it's very important about how color is perceived and not how color is really realized or synthesized. So this is also very important, and therefore we can have soft-proofing systems, so images or displays matching surface colors illuminated very, very accurately. Yeah, as I said, D50 was used as a light source which averages and which was used to not only say, remember the slide before, we have incandescent color and different light sources and everyone must specify their own value. No, we said in the graphic arts, we use this D50 light source from the beginning, from viewing booths, from capturing, from reproduction along the food chain. As I said, 3 values like LAB, or there are XYZ values also. They are a little bit older, and I skip them right now. And that means we have different ways to present this kind of color. You see, this is the LAB visualization, the L axis, the A, and the B one. We will see them quite often today. So you see every color we can perceive. Normal sight people. As I said, 90% of the men are normal sighted, 10% are color deficient, not color blind. You are color blind if you only see black and whites or grays. Most people, those men who bring the green strawberries back, those are red-green deficient, which are not able to become an electrician or a locomotive driver or a pilot or this kind of stuff. But most people are color normal sighted, and I'm always speaking about them because all the foundations, the colorimetry foundations, are derived from the normal sighted people. Okay, and so any color we are able to perceive can have this unique position here. The dark colors here, the light colors here. There's a gray axis, the neutral gray, near neutral, and the chromatic colors are here. And you can see that when you look on top of it, you have 2 different ways. When you see, you have like an orange color here, which is quite saturated. So here are the neutrals, here are the saturated colors, and you can see, okay, you can use the A and the B value to say to identify this kind of color locus, this location. Or you can say, no, I learned in math, you can always say this angle and this saturation. So with those 2 kind of variables, like the angle and the length here, you can also specify the same point in a coordinate system. So, and this is more intuitive because here you have U angle, and U angle corresponds to the U we see, like red, and yellow, and green, and purple. Because the AB coordinates, you really must work with them quite intensively, 1 to 3 years, to understand where an LAB value is and what does a -50, -60 mean. Most people just give up. So, but if I say, yeah, we have a 90 degree, then we know, okay, it's here. It could be an intense yellow or a very light fade yellow. So it depends. It's easier to identify. But there are 2 ways, different ways, specifying the same. And just for instance, in HKS, a spot color here, popular in the European or German area, if you take a measurement device and you measure this kind of color, and you will always see directly here that we have already in the CLAB specification the light source, because illuminating that sample with a different light, as we have learned, will result in a different color. And if it results in a different color perception, it must have a different color value. So that's why we mostly try to identify exactly the measurement conditions to be very to be concrete in the way we specify LAB colors. Of course, we have standards, and that makes it easier, but we will see later that there are different options to specify colors. Any idea for what the WB stands for? It's white backing. So we see that many objects we talk to are not opaque. So if you talk about this You see already here, there's a difference between putting an object on a white background or an air background, or if you look flags outside. So talking about colors, if I ask what is the red, when I see the red over white or the red over black, you can see here there's quite a strong difference, and it's still the same red. So it is important when measuring color to think about what are the measurement conditions under which we measure those kind of color objects. And that's why this is just an example to see we have a 60, so that means from 0 to 100 it's quite medium light. It is minus 57, so we are on the left side here with the A. We are 59 in the B, so I see this is someone around here. So this helps a little bit to identify, to understand what such an LAB value is all about. And starting with color, starting from general stuff, we see, okay, when we have an image and we have a profile, which is nothing more than mathematical descriptions linking the RGB values of your camera to the LAB values, which happens to be the one of your scene. If you go here and you have an accurate calibrated camera, then more or less the LAB values you get from every pixel is very close to the LAB value of that scene. So you have your RGB separations here, and your profile basically links this RGB values of your camera to the location in the color space. And you see here directly the first visualization of an LAB color space. You see this is the Gamut, which is a mass, a collection of all colors which can be reproduced in a device. So you see here ISO-coded, which is the name of an ICC profile which reflects offset printing. And it tells you, okay, what colors can be printed in offset printing on coated paper, for instance. You see the white point here, it's not perfect because you still have some leftovers between the white paper and perfect white. It's not perfectly going to 0,0 in the dark, so you have some shadow problems here. And this is the area of colors which can be reproduced by this specific printing process. And you see there are many colors, like exactly the orange ones here, of the roof here, which are out of Gamut. Yeah, so if you compare the colors, if you go there in Croatia, take this tile and go back to your print shop and say, I would like to print this tile accurately, the printer must say, I can't. It's physically not possible. It's out of Gamut. With my process, I can use hexachrome, I can use high pigmented inks, I can use better paper, and then we can talk about it again. But given a different process, there are limitations to colors. So that's why it's important to find a way, how do you print those colors? You can say, okay, I make an X and say I am not printable. That's not very sexy, and people normally you don't do this. So you map the colors inside the achievable Gamut in order to print them. And this is called Gamut Mapping. And there are different strategies to do this kind of Gamut Mapping. So to go from colors defined from your CI photo book, your Reflex blue, or your Pantone orange, or whatever your tile, your measured T's, or whatever your original is, and then you see is it inside the Gamut of your display, is it inside of your digital cinema, is it inside your Gamut of your tablet PC, you name it. So it's very flexible. And on the output side for printing, typically you come with that kind of colors, you see the Gamut, and then you say, okay, please give me the CMYK values which result in the same colors or in the most closest colors when printing to that process. And that is done by the output profile, ISO-coded for instance, and this gives you the separations here, CMYK, which printed with the printing condition which is defined here, matches to a very good extent. And we will see later there are different ways of doing this transformation, and this is called, since we talk about rendering and since there are different guidelines and different strategies, we call those guys rendering intents. Have you heard about rendering intents? Who knows some rendering intents? What?
That's
just one.
A strategy, for example, relative colorimetric.
Relative colorimetric, what else?
Perceptual.
Perceptual.
Saturation.
Saturation.
Absolute colorimetric.
And absolute. More than 4?
Soon.
Soon.
Relative with black point compensation.
Relative with black point compensation. Yeah, that is not. We will come to that later. That is not something defined by ICC. This is an Adobe invention, and they added it to the for rendering intent, so it's basically a fifth one, and we are currently in the process to unambiguously defining it. So, that is how it works normally. That is how color will be mapped. So you have your starting color. It will be mapped in the color space. You see some colors are inside the gamut, some are outside, and now you're mapping it. And that's what happened inside a CMM, a color matching module, which does this transformation. You see here the sRGB gamut, where the colors come from. You see the printer gamut, which mostly, but not necessarily, is smaller. People say RGB is bigger and CMYK is smaller. That's not the case. It's mostly the case, but there are always areas, especially in offset gamuts, which are bigger than sRGB gamuts in the cyan region, for instance. So one more time to see what I mean. You have your image. You see how it is encoded with the source profile. The source profile tells you exactly what color are the intent of the creator. And then you see, okay, where do I map my colors to? And now I choose a mapping which is appropriate for the purpose, and there are different ways of doing that mapping. And then we have two processes. One is the color mapping and being inside. What else do we have to do? What is the second step after the colors are mapped? After the colors are inside, you need to do the separation. So you need to decide, is it a long black, a short black, or which kind of black values you can use. Because we have CM by K, so an overdetermined equation. That means I can print the same gray with 0, 0, 0, 50 or 51, 41, 41, 0. So extremely different driving values giving you the same color. So that means we have different, and all the values in between, we have different values which achieves the same color stimulus, the same color perception. So that's why the creator must define which separation is the best one. So this is in normal words, input transformation render the colors to the PCS, the profile connection space, our LAB system, and from LAB the output transformation applies gamut mapping, re-rendering, and separation. So that color management approach is called smart profile and dumb CMM. So all the intelligence is inside the profile, because the profile does all those kinds of gamut mapping, rendering, and separation. So if everything is wrong with your image separation, it's not the ICC's fault. It's about the software vendors which populate, which fill the ICC profiles, because ICC is just providing the framework, the tables, how to format, the data structures, and so forth. If you fill in bad data, like a spelling error in a PDF, it's not the problem of PDF, isn't it, Olaf? Okay, so that is the same with the wrong ICC profiles are the responsibility of the creators of those ICC profiles. And having a look at of color in a general way, what we typically see is that we have RGB values and think, this is my RGB value, it's kind of clear, I see it on my display, I would like to have this red. But we have to see, or we have to learn that this kind of color reproduction is not very unambiguous, because if you do this, if you have a CMYK image and send it to 20 service provider, you get 20 originals back. Because 100% cyan is 100% cyan, but it looks different in different papers, it looks different in different inks, different processes. So that's why just having CMYK or RGB values, we call them device dependent, because they depend on the device. Just go in the supermarket and see your 100 screens, displays. They're showing the same source, the same RGB, but they all look different. Yeah? That is what typically happens, and this is for the displayed here. For different printers, the same CMYK sent to different devices, and everyone prints his cyan or his magenta, but it's not really consistent. All of them on an individual basis with a skilled printer can be tweaked or modified in a way that the printers or the print buyer is more or less happy, but if you ask them again to do this, you will end up with something different again. So that has nothing to do with color consistency, but still this is the way many colors are rendered on our planet, and people are not frustrating about it, because as I said, 90% are looking for pleasant colors, are not really remembering the originals. Mostly you don't see the original next to it, like your teeth or your car. So if you just see a reproduction and you don't see the original, you just rate it as is in isolation and not next to your original. Yeah, let's sum it up with respect to color. Color is an impression, like taste, feeling, and hearing. And visual perception has disadvantages, of course. It differs from person to person, age, mood, smoking. There are a lot of contributions to our ability. It depends on lightness. It depends on the color of an environment. If you know those guys, like normally you would see that this gray, and compared to that is darker, lighter. What would you say? The B.
There's a B.
You can use your eyesight. So it is actually the same RGB value. If you download my presentation and you go color picker and look up to the values here, the RGB values here and here are identical. The same here, blue and here are identical. So the physical stimulus, the physicist who measures the same reflectance, the same reflectivity, the same photons entering our eye. But the perception tells us something different. And that is very important to understand that the human visual system has, of course, a sensation, what happens up to the retina, but it has a cognition part on top of it, which supersedes our sensation. And that's why we have difference between sensation and perception. Sensation is the first part at the retina, and then we have perception, which happens in our visual cortex back here. And basically what our eyes needs to know is not saying, I need to know exactly what gray value it is, I need to detect the tiger coming from the background, otherwise I will not be alive anymore. And here you see simply, if you have an object here, and the same photons are reaching your eye, but this is in the shadow, obviously, this object must be much brighter, just by logic. If you have the same photons from here and here coming into your eye, the sensation is the same, but your cognitive part says, if that object enters the same photons like this, but it is in the shadow, it must be brighter. And that's why we perceive it brighter. So that's why it's important for color communication to see the color measurement values are nice, but the color perception is always depending on the neighborhood. And that is very important. The good thing for graphic arts is that we mostly compare images with images. And that's why the side effects, the neighborhood is mostly the same. But still, you need to know that you should not wear this kind of t-shirts when working color critical, because that reflects always also the samples, and you should take care of the environment you're working in. And here, this is a very simple example. The delta E between them is the same than here, but here the color difference is different. And in order to have objective methods, because when we want to communicate, we need standardization, which says, okay, please use the gray background to have at least as possible influences. Please use D50. Please use the 2-degree observer and not different observers to kind of looking for the best average for color measurement and then color communication from the print buyer downstream to the print shop. And here we talk about color appearance models, which kinds to simulate this kind of fact, but this is out of scope for the presentation today. So now we talk about spectral colors in the title. We have not said spectral so far. What does it mean? Is then one set of LAB values enough? And as I said, these three values unambiguously define the color appearance, but only under one set of illumination. So if you have one object and you define it, and you light it here, illuminated, three parameters are unambiguously correct to identify this color appearance. But it does nothing, it tells you nothing about what this material looks like if you look at it under different illuminations. Or it doesn't tell you how this material looks if you look at it with a different observer. So that's why it is important to understand that the LAB values defines colors for very defined environments. And that is the most important thing, the interaction of light, and we will see it later with a few examples, that if you want to communicate the color of an object, you need to know more about the objects rather than the appearance of the object at one certain constraint. And that is the link to our alexandrite at the beginning, our gemstone, which looks reddish on daylight and greenish under incandescent light. So that means if you have a camera which captures this gemstone under daylight and it looks reddish, and then you take this reddish LAB and you reproduce it, and you have a print of this reddish gemstone, and then you have your gemstone next to it, what do you think if this goes now to incandescent light? The gemstone becomes green. What happens with the red print? Stays red. So that is because it still has this magenta ink on top of it. That means that we must understand the difference between material properties and the result of the interaction of light hitting an object, being reflected and perceived by the eye, and then defined by an LAB value. And that material property is the spectral reflectance curve, because that is really what happens on the material part, the reflectivity of every wavelength across the visible spectrum. This gives you the information of the material property, because if you know that, then you can estimate or calculate how this object reflects incoming light completely different from a laser line to a broadband to an LED backlight, whatever. And that is the basic benefit of this approach. You see how it is typically working. You have a light source, you have a prism, a creating device, and you see typically a rainbow from 400 nanometers to 700 nanometers, 555 here in the middle, the green area, and you have a measurement device, and that can measure this kind of, as a light source, illuminates the sample, see the reflected light, and see what kind of wavelengths are in the reflected light. And just for example, if you use our HKS sample here, this is the spectral reflectance curve and of that green sample. That means it doesn't like green, so it reflects green and very much in this spectral wavelengths, but it reflects a little bit of the red and orange area, and it reflects almost nothing in the blue area. So it absorbs that energy, it absorbs much of this energy, and it doesn't absorb this energy. And this is kind of the spectral fingerprint of each material. This spectral reflectance curve is really a fingerprint, because using that information you can calculate how this object will look like when seen by a dog, how this object will look like seen under incandescent light, how this object will seen when look like or observed under different conditions. Because you see it already, these are the white backing values, but when you have your measurement device, you can change the settings and can say, oh, give me the D50 10 degrees values, or give me the A values, how this sample looks under illuminant A, the warm, and you see here it is -47, -49, it goes in the reddish direction from the color perception point of view. So, and much more. So you see, having this reflectance curve is this one piece of information which reflects the properties of the material, and based on that spectral reflectance curve you can calculate densities, you can calculate LAB values, you can calculate X, Y, Z values, you name it. And the 52-degree LAB values is just the one which is used for a standardized way of communicating color in the graphic arts.
Excuse me, what
Sure.
what are the 2-degree or 10-degree?
Good question.
stand for?
Anyone? Does anyone knows? 2 degrees, 10 degree?
The angle under which I perceive the light reflected, or?
That's a very good question. It is, when you look at our retina, we have the fovea centralis, a very local spot here where we actually have our cones. And the cones, the three cones are sensitive for color, not the rods, which are active for dim and black and white. And that area is very limited. That means only 2 degrees. So if you have a long arm, your thumb, and this is approximately 2 degrees, which enters your eye. And this projected, it could be this kind of here, or it could be 10 kilometers away. It is really projected on my retina on this kind of area where I'm able to see colors. If I see a big area, like if you see this white wall here, I see much more than just 2 degrees is exposed to what I see. and then we have rods coming into. So the sensation part will become four-dimensional. So we have the 3 cones and rods, and that means if you do the experiment, the matching experiment in 1931 and before, the color matching functions coming out are different. If you do the experiment on a 2-degree patch, what they have done, you get this point of color matching functions. If you do the experiment again with larger patches, you will end up with slightly different color matching functions because you're entering all the different types of cones. And that's why it has nothing to do with the geometry you measure. That is what people often confuse. It has only to do with the way you are calculating the spectral reflectance curve. I show you that in a second, how this works. So that is important because if you you enter this if you see a small sample swatch book and you use your color for painting your house based on the swatch book. Never do this.
Okay.
Because you will then see the difference on the 2-degree perception. It looks completely different if you see it in a huge wall. So that's why people use your 1 by 1 meter and tell you this big size, because then you need to do, or you communicate a 10-degree. But for graphic arts, normally we talk about fine details, small objects, skins, modulation, whatever, and that's why the 2-degree much more resembles what we do in the graphic arts.
So the rest is, the brain is making up the rest of it?
Of the rest of what?
Well, if you look at the spot on the white
Yeah.
board or whatever, and you see only part of it.
That's right. That's right. If you see here and you concentrate here, I can make an experiment coming from the side. You see it as of here right now. Yeah, because the brain is just able to see the very small part of the area very sharp, and everything will be interpolated. So if you see what happens really inside the brain, it really moves very quickly around different places, but actually you just have a very small portion which you see sharp. So it's a really fascinating system happens. So this is again one slide about the density. You might know about density also. This is used for process control because it just measures the way how much of ink is absorbed for a typical offset printing process normally. But this is a very nice example. We have a reddish sample here, a greenish here. These are the spectral reflectance curves, completely different. It reflects red and yellow, and that's why it looks orange. Yeah. But here, for the density filter blue, for instance, the density here coming inside gives the same result. So both samples give you the same density. And if you talk this with the telephone, I have density 1.6, and they have to say, yeah, 0 difference, perfect match. So density is very good for process control if you know what you do and you would like to see is it more or less of the same. But it has nothing to do with color communication. You need at least our 3 different parameters. Here's for the math people, what really happens. So we have a spectral radiance factor, so a spectral function of the sensitivity of the light source coming in. You have your spectral reflection of your sample. You multiply this, and this is the stimulus after the reaction. It's a simple multiplication, so the light entering your object. And if you have much light here and less reflective, you have less one. If you have much light here, much reflectance, much. If you have much light here, but 0 reflectance, 1000 times 0 is 0. Yeah. So this is the stimulus entering our eyes, the combined information of the light source and the reflectance. Think about the apple and the sun. This is the sun. This is the apple, and now this is the physical, measurable stimulus hitting our eye. And then we have our color matching functions, the result of the experiment, 2 degrees in this case, and then you just weight them, you do the integrals here, and that gives you basically the x, y, and z values for the 2-degree color coordinates. And then you do some math here, and with that you will get the CLAB values. And for those who are interested in that, I can give you the details, but it's just important to know that those x, y, z values are nice for coding, for specifying color locus, but they are very weak in explaining the color differences and explaining areas being overlapped or not and this kind of stuff. So that's why for color specification it's very nice, but LAB is much more reflecting what we actually see. This is a collection of typical light sources, which you can see. So we talk about our standard light sources, D50, D75, incandescent light source, so much red, less emission in the blue. We have different discharge lamps here with very peaks here. They are also very important in color rendering, because if you have such a peak, it can really change appearance. And that's why when you talk about color critical, you might have something like a Metamerism strip, which you can use, and that is compiled of different objects, or two objects with different reflectance curves, and they are made in a way that seen with D50 they match, and seen with something different they mismatch. So here I can see clearly they mismatch visually, so I know the light here is not D50. I can call it bad light or wrong light, but that is not, it's just awakening. No, it's not D50 here, so I would not judge, I would not critical think about colors or in a graphic arts condition under this light here. So those kind of small helpers allow you to understand color first, because this is a very good thing to introduce Metamerism, because Metamerism comes from the Greek. It says it matches under specific conditions, and they are constructed in a way that for this illuminant, for the 50, those LAB value matches, they're almost identical, but for different light sources they mismatch, and that helps people to not use a colorimeter. They can use your eyes as the best difference perceptor, as we've talked about. So that is when we go out in the break, I can give you the stuff, and you can see that it looks almost the same when you go to daylight.
So you don't need to be a Lufthansa frequent flyer for that?
That's right, you can also be a senator or on circle. Okay, that is important to understand this concept of Metamerism, to say not only one reflectance curves can add to the same colors, even different can do so. And understanding now the interaction of light, reflectivity, and observer, we see that there are different concepts or different phenomena in our industry. And two concepts which are very often confused are Metamerism and color inconstancy. Metamerism, as I said, is two colors which match under one condition but mismatch under different conditions. Like your print and your proof might match under D50 but might mismatch under illuminant A, or mismatch under incandescent, or whatever. Another example which is related but different is color constancy. You have one, just imagine you make a gray, you print a gray with 50, 40, 40, 20 cm by K values. We call it a composed gray. If you use that one and see it here, it might look a little bit reddish gray, and then you go out, it's a greenish gray, it might look a neutral gray, and then compare it when you print it with a 50% K only, which has a very flat spectral reflectance curve. Then you will see that those kind of print looks almost neutral under this light, this light, this light. So a sample being perceived as achromatic, or being perceived as the same color, we call it as color constant, because the color appearance does not change with different light sources. Where we have color, and this is only understandable if you see the spectral reflectance factor, because if you just see as the LAB value, like a 5000, the neutral gray, you don't know if it is made up with such a reflectance factor or with such a reflectance factor. So if you have a spectral flat reflection, which is typically the case if you use this black only channel, then you have a very stable perception of grays. And that is, and that's why people use a GCR, gray component replacement, often in printing, to have more of the black and less of the chromatic channels C and Y, for much other reasons also, but this is one reason to have more color constancy in your reproductions.
The definition is just the one talks about the material spectrum and have different light sources, and the others to have different material spectra. and under the same light source.
You
It's just a difference.
You can use it like this way, but the main difference is Metamerism is only about 2 species, 2 samples. Color constancy is always about 1 sample. That is the major difference, because you can compute the Metamerism index between different observers. You can compute Metamerism index between different light sources. And here the same. You can see, let's say, color constancy in the D6511 means how much changes, or how different is the perceptions from going from D65 to F11, or going from D65 to A. So you can combine the 2 combinations which you would like to combine, and then you must make the math to evaluate this kind of color difference. But we've talked about color difference in the delta E's. Does anyone know where the E stands for? What is E? Delta E? Intensity. That would be German E. It's A, B, C, D, E. Any idea what delta E means? It's one of the German abbreviations. It stands for Empfindung, perception. So the perception in German is Empfindung, and this E is, so if you have 2 colors and you would like to see the difference, because mostly they are not matching perfectly, they have some difference, and if you would like to see the difference between 2 colors, 2 perceptions, as we have learned, it is a difference in perception at delta E. And you would like to rate them, and mostly we would like to decrease the delta E, the color difference between the soft proof and the hard proof, or between print and over the production run, or from left to the right, or you name it. And that is what typically happens when you see it outside. Yeah, you see like the same sample looks inside and outside, and they appear differently because of this kind of metamerism. Or the same here. This is the physical sample which is really hanging over this guy, and this is the print. And illuminated in the wrong illumination, it looks different, and that is metamerism. In that kind, if you are the print shop doing the print reproduction for this, you must ask under which light source this print will be viewed later. And if it's not D50, you must do a preparation for Karstadt or whatever light. But you see the mismatch right here, and this is how metamerism is viewed in reality. Or very nice stuff here, if you have retouchers and you don't know how this Picasso or whatever has been painted under, but you see there's something to break, and you just see it under incandescent light, and the people 200 years before just had just incandescent light at night, and so they fixed it, and it looked the same for them under incandescent, but they never changed it for, they never viewed it under different light source, and then having different paints, because some pigments like lapis lazuli are very expensive, so you use cheap pigments, other pigments, which give you the same sensation for one condition, but a different sensation for another, results in this kind of stains here, just metamerism in reality. So, spectral information, next chapter. So, when we now learn that having the spectral information, we would know much more about the actual material, about the actual object, and not only of the perception of the object, which is LAB. So that's why you can capture spectral information, like this color checker you might know, and if you have such a camera, a multispectral camera, there are a lot of them available, you will get not only RGB or LAB values, you will get spectral reflectance curves of all pixels. So imagine an image 2000 by 2000, not by 3, by 36. 300, 400, 410 nanometers, 420, 430, 440. So going from RGB image science to spectral imaging, we have not 3 dimensions, we have 36 dimensions. Of course, they are highly redundant and we can compress them, but at the first sight, we increase the amount of data which is needed, because RGB is very sexy, just 3 channels. If you have to store or carry around with you the spectral reflectance curve, where you need at least 36 points to reflect what's going on in that material, you need much more information. What you end up here is like different gray or black-white channels, where you see what is the reflectivity here, and at 420 you can think about, okay, at 420 I expect the blues being reflecting, so being light here in that black and white image. If you see here more in the green area, 408 in the green area, you expect green objects having a high reflectivity, and you see it here. Yeah. Going to the red area, so you expect that the red is reflecting very much. So this is spectrophotometer, which gives you 1 million or 2 million spectral reflectance curves with one shot. And that is a lot of data to save. That is spectral information, multispectral imaging, and it is an entire scientific field in the community, and we think about, or they think about, really conveying those information from the capture to the end. And we will see now, right now, for those who do the math, yeah, 2000 by 2000 by 36, and just saving it in PDF, maybe 60 bits. 16 bits, it's quite huge PDF. So that's why, and seeing the benefits of this spectral reproduction, we see that this is this multispectral imaging is mostly done in niche markets. You know, if you have melanoma detection for skin doctors, you need that information. If you have archive for this kind of Picasso work, you need that. But for typical leaflets or typical reproduction of images, these RGB and D50 LAB are mostly fine, and we will come to that later. Oh, I forgot 700 nanometers. Yeah, so as I said, CLAB values represent the appearance under one set of conditions. Spectral values represent material in information. For fluorescent samples, it gets a little bit more complex. I would like to finish the presentation here, and if we have time, we can talk about how much our optical brightness being put more and more in our papers will change the story, because then it's a little bit more depending on the light really exhibiting or exciting this kind of chemicals, but for non-fluorescing samples it's quite easiest. So what are the benefits of spectral values? What does, what they allow us? They allow us calculation of color appearance under different light sources. So if you have spectral reflectance values, and now more for single patches rather than for entire images, you can calculate how this looks like. Luminant A, luminant D50, D75, S11, or even my house illuminant, because I just measured it with my I1. You can measure it for 2 degree or for 10 degree observers or different observers. And so this gives you a lot of flexibility in prediction. Calculation for different observers. It is very important, and that is the main topic for the talk at all. It allows you to apply physics, because if you understand what's going on the material level, it allows you to model what's really going on, like what happens with the photons entering the different layers, the interaction of the different refraction going on. And so this is the main benefit of this physical information for the remaining part of our talk. It's for commercial printing, it's mostly CMYK, and we talk about spots as solid. So in commercial printing, you have a 100% Pantone Reflex blue, or Deutsche Bank blue, or Coca-Cola red, but it just mostly is solid at a different size in the logo or whatever. But we must also think about two more complex use cases, which are tints, 50% HKS14, 50%, 60% Pantone Reflex blue. Or even the next complexity is how is the interaction of spot colors being printed with process color, or how does 50% Pantone Reflex blue looks like when printed with 70% Pantone orange, and how does this looks like when you change the ink sequence. Yeah, and these are use cases we will talk about in the remaining part. Package, it's much more fascinating, and here we actually talk about ink mixing, different ink sequences. So here we have much more flexibility in what's going on, and that's why I think that this spectral information is much more beneficial for packaging applications and not so for commercial applications, because we all must ask ourselves, is the pain worth the gain? And for commercial applications, we mostly see that this spectral information are niche information, and very important for them, but for the packaging, we'll talk about a little bit more. Is it really a brainer? Going a little bit into the physics, and if you want to understand what's going on under the hood, if you are a photon and you are entering this kind of layer, what happens there? If you have different layers, if you have half-toning involved, if you have substrates which are scattering, if you have substrate where the light goes through, what happens with the backer? Is it reflected? Is it partially reflected? Is it absorbed? So you see, what happens to photons is you can have the specular reflectance, like a mirror reflectance. We have absorption. Absorption is just absorbed, converted to energy inside different wavelengths. We don't see it anymore. Reflectance here is scattering around. You change the direction and it re-emits somewhere different. That is the reason for the dot gain, the optical dot gain actually. Transmission, it can go through directly or here. Fluorescent, you have light coming from one area of the wavelength, like blue light or 360 nanometers, and it re-emits later. So you don't see it as blue light anymore because something goes on here under the hood. It's the same when you drive a car and you open the window and you put the arm out. This one gets brown or tanned, and this not, because here you have this UV energy coming and on the right side not, or the different way around if you are in the UK. So that is the same principle. And that helps you here to understand what's going on. And if you have just x, y, z, and you have seen the math before, you just talk about 3 integral values. And that's very bad for really modeling the physics, modeling the interaction of light in the different layers of what we do here physically. And that is the main benefit of conveying spectral information from the front to the end. Okay, spectral modeling, I think a 101, very brief class of spectral modeling. If you want to enter that field, it's like mandatory information. If you want to do spectral modeling, that means I give you a spectrophotometer, an I1 probe, and I give you 2 colors, let's say it's 100% cyan, 100% yellow, and I ask you what happens if I print them on top of each other. And I don't print it, you must estimate it. How can you tell me the outcoming color? What can you do? And there are very easy and very complex models based on those information. So the question is, if you want to model the spectral reflectance curve of some interaction of 2 or more inks, you need to understand what's going on, and you need to understand at least the inks involved. Yeah, is it 2, 3, 4, and the number of the C-lab values of the solids. You need to know at least the LAB values of 100%. We will see that it is much more beneficial if we have some information about the dot gain, because even in commercial printing, spot color rendering is not defined at all. The TVI, the dot gain for spot colors are not defined. Even not in 12647 or other standards, no one defines which tone value curve you should use for printing a Pantone reflex blue. 30% dot gain in the middle, 10%, it's not defined. And therefore it was very hard to allow for this PDFX, for this printability of that information. We'll come to that. So you need at least the inks involved, and you need to know the opacity. Because if you have an opaque ink and you print it on top of it, you don't care about what comes before. Yeah, that's very easy. So if you have opaque inks, like the PostScript or PDF model, graphic models in the basic step, it's just opaque. The top one is ruling out everything else. That is very easy to understand. So if you have, but mostly in our world we talk about transparent inks. Otherwise the whole system doesn't work. Yeah, so that's why 99% we talk about with transparent inks. So the opacity is not so important. But of course, if you go more in the spectral, in the packaging market, and you see different inks, they have not perfect transparency, and so the way of shining through, the amount of ability of shining through, is this kind of opacity value. And opacity, if you look in 32000 part 1, it is implementation specific. So you don't know it basically. That's not good for unambiguously rendering PDFX files with set information. That is very minor, and most people have to look. So Adobe, when rendering those kind of colors, they have nothing more. If you just have an artist or just using InDesign having 100% HKS40, which is Fogra red, and you make a tint of 60%, you don't know, and Adobe doesn't know the TVI. It has a model inside, it has an average TVI expectation, and renders the colors on the screen or later on the print based on that assumption. But they are just having the LAB values from the library, and in the library they can't look up for a TVI. They can't look up for an ink sequence. It's not defined. So that's why you end up having spot colors not being as a solid, but as a tint, rendered differently, and no one can complain because it's not defined or not fully defined. So now we come to additional information. What kind of additional information are helpful for us to improve our prediction? Okay, the tonality, the dot gain. If I have this tonality, what is the dot gain of my reflex blue or magenta or what of my process colors and my spots? I have much more information about the final overprint. Spectral information, so not only the LAB of my HKS40, I would like to have the reflectance curve of my solid, because that allows me much better modeling and prediction of when I know the HKS40 Fogra red spot color, if it's over printing with 50% magenta and 20% yellow, because my designer has composed this kind of combination, I'm much better in actually predicting what's coming out when I have the spectral information of the solids. The ink sequence is very nice. Sometimes people change ink sequence and then they get a different result. Why people change ink sequence? What do you think? What is the typical ink sequence in offset printing? Do you know the sequence?
I guess K last.
No,
K.
K first.
K first.
From dark to light. In offset printing. K, cyan, magenta, yellow. But sometimes the physics of interaction often results, especially if you have skies, blue skies, the level of ink trapping results in kind of a modeling. And sometimes in commercial printing, people change magenta and cyan to reduce the modeling. But if you reduce them, you get less modeling, so macroscopic homogeneity problems. But the ink laydown is different, and the resulting color is a little bit different. Of course, red doesn't turn green, but the correct color looks a little bit different. So ink sequence is also important to know when predicting the final appearance of your color. Recipe, that might also be interested if you know the recipe of a color. If you know, okay, if you are in flexo printing, for instance, people give you files with 20 spot colors, and mostly you don't have them. So that means ink formulations, that you have an ink kitchen, yeah, they call it ink kitchen, and they now start to say, okay, how can I match with my available inks that kind of colors, or maybe two colors, and they have some recipes, 50 gram of this, 20 gram of this, or milliliters, and then mix it, and then have a new color which I can use as a single color to reproduce that appearance. Special effects, this is like opaque white, which is often used when printing on transparent foils, OPP foils and this kind of stuff, or metallics. This goes one step further. You can get the pearlescent interference pigments. This is out of the scope today, but you always get an idea of when we enter more complex scenarios, the prediction of the final color appearance of the printed matter gets more and more complex. And the question is, do we need to convey information to allow the creator, when rendering their content, more reliably to what actually ends up later. Yeah, and measuring values other than the 52 degree might be also beneficial. So this is the standard in the graphic arts which defines how to measure, and it says use D50, UD degree, but graphic arts is the only industry which use D50. If you go to paper industry, they use D65. Motion picture industry use D55. So we are the only one using D50. Any idea why we are using D50 in the graphic arts and all the people are normal and use D65? Are we so crazy or just?
We love outdoors.
D65 is even more outdoor. It's bluish. It's more outdoor. So that is not a good reason. That would go for the 65. How did we rendered? How did we viewed originals in the 1950s, in the 60s, in the 70s, in the 80s? We had slides, and we used it with an incandescent projectors. So all the slides, all the originals coming in the retro houses would be slides viewed with an incandescent projector. Yeah? And so we have to talk about 3000 Kelvin. So we talk about warm, bright, candlelight, color temperatures. And if the originals are rendered there at this 3000 ones, it is very hard to match it for a printer. So that's why they said, okay, outdoor typically the average is about D67 or D75, 65, but indoor the best average is D50. So in the graphic arts in 1976 I said, okay, of course the average of all viewing conditions is more to 65, but we would like to not force print shops to use two different light sources, 3000 and 6500. We would like to get a compromise and meet in the middle, and that's why the D50 was the best average for really outdoor average viewing conditions, and the 3000 Kelvin where we came from. So now we can technically say we have no slides anymore, we don't have any incandescent projectors anymore, so why we bother and just skip it. Technically you can think about it, but practically we have a huge historical backpack with this information, all the aim values, ICC, PCS is defined on D50, so it's a long list to change now. So that's why, for consistency reasons, we stick with D50. Let's give you an overview of the use cases. So what use cases are there which can benefit from our spectral information we have talked about so far? So, of course, they can use in a very manifold way. There are different ways. Implementation depends, of course, on the objects which are described. So you can talk about spectral reproductions of images in case of spectrally defined images. This is typically the case for artwork, cultural heritage. So if you go to the Meadow Foundation in America, they have spectral scanners, Lumiere art in France. They capture Mona Lisa and this kind of high-value pictures on a spectral basis, and they end up with a very huge data set. And they use it for archiving, of course, but they also, because then they can really render it how Picasso has seen it under luminant A. Maybe they can render it how Picasso has seen it under daylight, how Picasso has seen it under this. If you just have the LAB, you know Picasso had seen it under D50, but you don't know any information more about the used pigments. If you have spectral information, you know that pigments. But again, as I said, it's a niche market. You can do a better simulation for single spot colorings for proofing purposes, for instance. So if you know that information, you have a CM/K image and you have an additional spot color and have this defined in a spectral reflectance way rather than just the XYZ or LAB value, you have much more ability to predict it more accurate for soft proofing or hard proofing. You have better simulation for altered CM/K processes. So it's often like Berlin for Postbank, I know that they have CM/K, but they replace the yellow with the Postbank yellow. So then of course there is a effect on, of course, all the colors which are where yellow is involved slightly depending on the difference. So if you have a spectral information, you can have your process color and you can update your color behavior based on the spectral information of your existing colors and the new one which you are replacing. You might know the packaging module from a Profile Maker. They're exactly using that model. They say, give me the spectral information of your CM/K, give me your spectral information of your spot color A, and then I can write you a profile which gives you the printering results when replacing that with one of those. So that is the functionality which is now available when you have this kind of spectral information. You can do the reproduction for different light sources, as I told you, and of course a better reproduction for different output processes which are not only offset. We talk about outputs which have different inks, like if you go to inkjet printing, they are having not the same kind of spectral reflectance curves because they are using different pigments. So it's, you have a higher level of accuracy there. And as I said, this is exactly what we have. This is a perception under daylight, and it really changes the perception for internal reasons inside the crystal here to a reddish appearance. And if you stick with normal D50 colorimetry, you will not get and you will not see this transition. This is of course an extreme case, but this is, I think, a very nice example which illustrates the power of spectral information. In the last part of my presentation, I would like to use something from Greg Reevy from FFEI in the UK, and he is the leader of a project we call Proposal to Add Spot Color to Support to PDF, and I build up the presentation here on his slides, just as information. So, when we talk about how the spectral information can be used for graphic arts workflows, I would like to differentiate or separate 3 different use cases or groups, because it makes it easier to understand, does it really help me in my specific application. And what we have, of course, are the entire category entitled spot colors. So we talk about when substrate properties are critical, because we're not only printing on paper, especially in packaging, we're printing on cardboard, we're printing on OPPs, foil, and different materials. And here we have much more flexibility and power when we have the spectral information. Films are translucent or clear and need backing, and that with just LAB values, it's very restricted and limited in predicting what happens on other films or other substrates. Hi-fi process colors, so that means if you not have only CM by K, you can have high pigmented CM by Ks, or use even 6, like a hexagon system that is typically called as hi-fi process color sets. This helps you also a lot when you have here spectral information. And post-print processes that impact color appearance. When we have ink on paper, it's mostly not, or ink on substrate, to be more general, it's mostly not finished. You have a lot of post-pressing coming, and that of course also affects the perception. Just imagine you have a matte foil or a glossy foil, it changes your dark colors immediately, or very intensively. So that's why it's also important to understand what is the kind of post-press which comes later, and how can I model, how can I predict the interaction of additional post-press steps to the final appearance, because the customer is mostly interested in the final appearance of the end printed product and not of an inline or offline process steps in between. Even that might be helpful for the printer to actually produce it, to have some pieces in the middle, but at the end the outcome is important. Lamination, backprinting, coating the film, just to name a few. So let's have a look at the spot color. So we have our 3 use cases, and now this is the easy case. This is what we normally talk with in commercial, or handle with in commercial printing. We have a spot color. The CLAB values are enough, because the CLAB values tell me how this color looks like under D50 2 degree, and if I know them, I can reproduce them with my proofer, with my Epson 48, and if the gamut is available, is big enough, I can really make a perfect match for D50. That's very nice, and we do this very successfully. But it starts already to the problem when we have tints. So when we have 50% of one spot, first, what is the backing? How much is the influence on the backing? And so the kind of opacity influence, and then what is like 60%? So how does 60% look like? And there, at the moment, there is no really no provision for conveying this information, and that will be changed soon. And this is the 3rd level of complexity, as an overprint. You might know this sample. Who knows the alternate test page? You know? Have you ever seen this kind? Do you remember this kind of test image? And do you know what they did? What mean think the authors did with the colors here?
They sold a lot of.
the concept of PDF is to have, of course, an encoding like a color name, but also had to have an alternate color space, and they changed the alternate color space to be from reddish to bluish, and so you can see if the engine is using the name with a library attached to it or the alternate color space, and this, since it looks extremely different, you can see it. But here, mostly we have just an interaction, so of a grayscale image and spot color lying on top of it in different tints. And the question is how the overlapping result looks like. And even PDFX has no answer to that. Even if you think about it, PDFX is always 100% unambiguously colorimetrically defined, as I like to call it, not in this instances. Because those kind of interactions are not unambiguously defined. And that is one of the reasons we did a research at Fogra for some years, and we have printed the main inks from Pantone matching system here, and we used linear plates. So plates where the tone value on the plates is the same, 50% of the data value, 50% of the plates. This is a normal process which people use as a starting point today, and you measure the dot gain. Yeah, you measure the TVI, the tone value increase of your different warm red. Those are the 13 basic colors of the matching system, where all other colors are mixed, are mixtures of those basic colors. And you see, like this, the purple one has just a dot gain of 23 here in the middle, but we have colors which have 45 dot gain. So you see, and since they are now standardized, like for CMYK, we have standardized them. Yeah, we said for this paper we have 30% dot gain, so everything is nice, and the output intent, the profile mimics this, and everything is nicely encoded. But here, for spot colors, there's no standardization right now, which says spot colors have to be printed with that TVI or that. If you get rid of them, you can easily propose something like, okay, all spot colors have to be printed with a TVI of this curve, something like this. You can do this, and this would reduce a lot of complexity, but you need to have consensus in the committee that that is a problem here. But that gives you an idea why the spot colors are so different, and they're using different recipes and different chemicals to standardize. And another thing is those kind of printing, or all kind of printing, are not very linear. That would be very nice, you know, if you have a CRT display, a cathode ray tube from the earlier times, they are very nicely linear. That means if you if you measure 100% cyan or red, and 90, and 80, and 70, and 60, and 50, and 40, and you measure it with a telespectral radiometer, your display, and you show the spectral reflectance curve or the emission curve, and you normalize it, let's say for the maximum, whatever, you will see that all lines are perfectly matching on top of each other because they're additive, and it's very easy. That basically means you just need to know one reflectance curve, and you can compute with one scalar, with one number, the reflectance curve of difference. This is linearity. But unfortunately, printing systems are not linear in no way. And if you just see the different, if you print a ramp of cyan here, this is the paper white, yeah, here, paper white, and then 100% cyan here. We see cyan is absorbing red, it is absorbing green or oranges, it reflects here, so it looks the way it looks, cyan. But when you normalize it to one wavelength, it actually doesn't matter to which wavelengths you normalize it. You see a lot of differences still here, which don't line up perfectly, and which is an indication that you can't simply normalize or scale the resulting spectral reflectivity based on just the paper and the solid. And also, you see something which is very interesting, the waves here. Sometimes you see the fingerprint, you see some waves here, yeah, which are not here. So if you just have one solid and you scale it somehow, you can, if you want to scale it with one number, you just change the amplitude, but not the character, the form. But you see, here's something going on under the hood. So the reflectance curve of, let's say, 30% or 70% has something inside which is spectrally different than, say, here. So a simple scalar is not enough. So that's why we need this spectral information to overcome that nonlinearity. And That brings us to our objectives from TC130. This is a technical committee where I'm working, which is active for the graphic arts standards, like PDFX, or in working group 3, where I'm more active for printing. And here, if you see the main benefit or the main scope of 15930.7 PDFX4 is to permit the predictable dissemination of a compound entity to one or more locations. Can you find the author of that sentence? It's very nice.
Dave McDowell.
Dave McDowell? Okay. It just say it's about predictability. Printing the expected. I translated to printing the expected. You would like to give the creator some mechanics, some provisions that he or she is able to predict what the service provider later will end up with. Because if you don't have predictability, you don't need standards at all. Because just to make it sexy, you don't need standards, you don't need Fogra, you make it sexy, but any sexy reproduction looks different from day to day, from space to space, or from location to location. So that's why it is the main feature of PDFX is to convey the color information and to give the creator already a hint or a very informative description of what he or she can expect later to come out. Because if it doesn't provide this, there's no benefit at all from a color science point of view, because just giving you a ticket, the service provider makes it nice or sexy, send it to 7 service providers, you get 7 originals. And that is for some applications okay, but not for the ones we are in. So this is the slides from Craig Reevy, where the use case is proposed, in this case for solids. You have a designer, you would like to create a printable product, that means a brand requirement. So you have a brand color like Coca-Cola red, and they have their definitions of their brand colors, and you can design, can be made or can be proofed, like a hard proof, validation print or contract proof, or on a soft proof with that information, assuming that all the parts are colorimetrically defined, because a proofer, being Epson 48 or an ISO display, is very lazy. It just renders the colors it's supposed to be, if it's inside the gamut. And so it's only about giving the proofer the right aim values to render. And then, of course, at the end, the package or the other product can be printed as the designer intended, and that is kind of the role model or kind of the basic schema what we would like to achieve. Having a closer look on how this design, this content is made of, you see there are a lot of spot colors used. So these inks will be used as a process inks, and in this case the Pack Pro blue will be used instead of the process cyan. And we already have talked about, yeah, what happens, what does it change? Are now my advertisements, which are representing my swimming pools, look different? Is it the blue now a reddish blue or a greenish blue? What goes on? And here the spectral information helps to recalculate the output profile, to update the output profile, and so to speak, if you change the output intent with that physical interaction or with that decision to change actually this ink, then of course you must create a new output intent. But for package printing and for commercial also, you can't easily go the normal ICC way, which is simply, yeah, no problem. Just take a target with 4, 5, 6, 7 colors, having 10,000 samples, all the interactions, print it, and then I measure it, make a profile, and then I use the profile. That would be the simple answer of an ICC color scientist in a normal way. But you say, no, we don't have money for such a print run. We need separation right now and not tomorrow, so we can't really do it. And that's why we are so beneficial or so successful with the CM/K printing, because this can be done once, and since many printing conditions are very similar and close to that, they can be very successfully mimicked and used with the ISO-coated profile, for instance. But for packaging printing, there's no chance to really standardize anything, because all the jobs are so different. And so we need to understand more about how this interaction works to then predict the outcome without doing actually a print run and saving money. So that is just what I said. It is extremely time consuming and costly to make such a print run, to measure simply, because if you do it actually with an experiment, you don't need to predict anything. But that's why the whole prediction, the whole color modeling is only to save this kind of time and cost consuming print runs, because if you do the math, you will see there are trillions of options in the interplay, and that is a very endless story to actually do this, especially when you have such different kind of packages. And just imagine the different possibilities, the possibilities if you change ink sequence. So it's very many. Or here, process ink characterization. That is just in practical steps what I mean. So you have this test chart. This is a CM/K test chart, and you measure it. You will get this information in case of really doing it. So now the sign is not the normal process sign, it's a Spectral sign. You can measure it, you can make a profile. This is normal ICC colorimetry, but of course it assumes that you actually print it with that. Normal people just exchange it in that typical workflows and expect you to print accordingly without doing that test print. That is a normal. That is not a normal case, because, as I said, they normally not make this test print. So just for you to understand how you can technically do it without modeling at all, but the whole modeling should really save this kind of step. Or another one, a spot set of inks. Each ink is a spot color. So this is another use case, not a CM/K process, which is updated. Here we have really a spot set of inks, and I think this is the main benefit. Having this kind of spots is the main benefit for adding spectral information, because each ink is individually characterized and it is used individually. So Coca-Cola red is mostly used as Coca-Cola red for the package or for a background. It is not used with 30% overprint of magenta or something like this. And here it is very helpful to have the spectral information when you digest, when an ESCO system or a GMG or whatever have to process this kind of PDF file. And how we can do this? Typically, what is done today even, you have a tint level, a tint ladder, so you have your solid, and you print different tints, like 10%, 20, 30, 40, 50, up to 100, and you print it over white and over black, because that gives you information about the transparency or opacity. That's very important. And with those measurements you can save it as an XML file, for instance, and or using for a different spot color. And with that information you can do the separation and printing much more efficiently. And that is what people actually do. If you talk about with packaging printer experts, they make this kind of RAMs and they save it in Excel files and ship this text or Excel files with their jobs. And the main benefit of adding this spectral information to PDF right now is to convey this kind of information as a metadata to be part or to become a part of the PDF. That is, TC plans to define a standard way to communicate spot color measurements, and that is a standard where we work on to get, or actually a family of standards, different parts, like 5930 also, to define the minimum information, because you need to define how many, and do you measure on white and black, on the wavelengths from 400 to 700 or 380 to 730, so there are many details which have to be defined. And this is basically the color exchange format from X-Rite. You might know that color exchange format. This is something where X-Rite is doing similar things like Adobe. They come up with a proprietary format like CXF, and they changed or decided to make this publicly available as an ISO standard. So what Adobe did with PDF, now X-Rite is doing with their file for color exchange definition. And now it is all about using those kind of CXF measurement data, being a measurement of an image, being a measurement of a solid, or being a measurement of such a spot color characterization, be part of PDF. That is, as I told you, that is the way people work today, and everyone does it differently. Yeah, everyone has this Excel spreadsheet and uses the reflectance curve over white, over black, see the color here, and get some additional information, extract some transparency information. Here's the TVI, here's the reflectance curves. This should become part of PDF. That is the main focus, to see not only to overcome our step 2. You know, the step 1 was just a solid, we can handle that more or less. Step 2 is the tints, with the tint levels also, and step 3 is a complex interaction with all the different things. And with that proposal, we would like to solve the step 2, where we can reliably communicate the color appearance of tinted spot colors. That is for some people who like to, or who love code, or to see how such a XML file can actually be encoded. I think it was 1.0, so we are now with 3, I think, something like this. But again, you get an idea if you're familiar with XML. Here are the reflectance values, the reflection from 380 to 390, 400, 410, and so forth. Yeah, and you get some a little bit more information. And that is more or less the data which should be communicated. And that is actually, no, do you see the red? So this is should be red. Yeah, the projector is very badly calibrated and not very.
I think the problem was before it was calibrated. It can be.
That's right. But you see already there are some red areas here, and when you are familiar with PDF and the output dictionary, the output intent dictionary, actually everything in black is existing, so we have it right now, and everything in red, which is actually proposed. And you see we have much more flexibility, we have much more ability to now have spectral data, to have mixing hints in this special dictionary where we have printing order, I called it sequence, where we have solidities defined, and where we have spectral data for the different spot colors we are actually using in our job. So that is a proposal from the TC130. And looking into the DIS, so it is currently a DIS, the 32,000 part 2. DIS actually means going from a group to the outer world. Now this DIS can be bought by anyone. Up to the DIS, it was only within the committee. Now it's accessible for anyone to have a look at it and to buy it before, of course. Yeah, I don't read it. I give you a short time to just read it to see how actually PFX data is now part of 32,000 part 2. Nach Zeit. Noch 10 Minuten. Okay.
7 minutes are over.
7 minutes over.
44 was over 44.
44.1. Okay. Okay. No worries. So just to see how concrete it is already. So we are not something proposing and hoping we will have it in 5 or 6 years or 2 years. It is something really concrete. We have it in the pipeline, and we are quite optimistic and positive. However, you see some may and everything. When you read a may in ISO, you think about a should or a wise plan or ought to, and this is really something that having metadata at all, it is something which is not a shell. That means even if you have that information, it's just step 1. Step 2 means to have consuming engines, processing PDF engines which actually use this information. So you can perfectly ignore it and you are consistent or compliant, whatever. So that is something which we have to discuss still, how much burdens, how much requirements you can put to conforming readers to interpret that information. Yeah, meeting the objectives. So we think having those kind of additional information helps exactly to achieve that goal, to print the expected, to use more practical words rather than the dissemination. Yeah, let's summarize. Spectral information provides additional information and information about the material properties rather than the appearance of one material under one condition. It benefits are not only for non-CMYK image content, because if you have properly used ICC color management, it's perfectly fine. So for commercial printing CMYK, you can really, the benefits are very small when going to spectral printing, because for the typical applications, if you're not a part of this archiving world for high quality cultural heritage, that is normally okay, but especially for non-CMYK image content, the benefits are really huge. PDF2 will be capable to convey this kind of information by means of metadata being CXF data. That's why there are currently no explicit requirements. That means, as I said, might or might not use this information. So that is something, again, where the industry then must a little bit motivate the vendors to use it at all, if they are deciding not to use it. But this is the chicken and egg problem mostly, to say, okay, I use it when the data coming with that information and the other way around. So hopefully we can overcome that. For specific use cases, as I said, it won't change, it won't revolutionize the graphic arts industry enormously, especially if you see for the new rich media and other functions. So I am blue-eyed, but in that aspect I don't want to be blue-eyed to see that really changes dramatically the way we work. It won't, simply. But for the customers, especially active in the packaging arena, they will get a very easy way to communicate and convey their information. What they do right now with very practical and very cumbersome methods. The existing way of color exchange won't be affected much, that is clear to say, and as long as there won't be clear requirements on how to use the information, printing the expected, as I call it, unfortunately stay a dream, I think. I asked in the preparation for that talk, Leonard, can we expect that InDesign just adds this kind of data and say, when I add HKS or Pantone Reflex, I go to my library and click it, and then instead of putting the LIB or the name, InDesign puts this CXF data inside and you can read what he answered to me. So it's a little bit frustrating, but it is realistic, so it's really depending on the customer base asking or convincing companies to do something. They don't do it for altruism, that's for sure. And that's why talking with other people, especially company players in that market like ESCO, Kodak, GMG, they said, okay, it's a very worthwhile step going forward, and they are not so negative, and that's why I would like to end with a more positive citation from Greg, where I borrowed most of it. And with that, I would thank you for your attention, and I'm hopefully open for a few questions to come. Thank you very much.
Thanks a lot, Andreas. Any questions right away?
Do you know what Pantone's position is regarding the spectral information? Because it has to come from them, basically.
They are currently in the process to releasing it. They are not able to tell me the truth or to tell me the actual truth, because they have a release date, I think in 2 or 3 weeks. I asked Tom Lianza, he was in the process and preparing it, and they said they are providing this kind of information, basically. So that is very helpful from their part, yeah. And that is one reason why they are putting so much effort to make CXF a standard, because going from a proprietary document to ISO is quite an effort, isn't it? Yeah. So that's why they don't do it without higher interest, and that is part of the story to use and convey their information in that format. Yeah.
Good to get new grayscale hair.
Yes, for white.
Any other questions? How does it compare to the ICC standard to introduce spectral data in ICC compiles? This is a XML-based format, and
ICC is working on ICC has in the current format it doesn't allow for spectral information at all, despite some private text. But ICC is working on new ways where to go. It's called ICC Labs, where they completely revolutionize the concept of the ICC with a spectral profile connection space, with information about how to model some device capabilities, not only to have tables, but they are not using this kind of information right now. They know what's going on and they work together on that one, especially Greg Reevy. He is very active both in ICC and in the graphic arts standards. But right now this kind of information is not enough for, or it's not one-to-one part for ICC labs. But anything right now in ICC labs is still work in progress, very open, and I think we won't see anything like ICC 5 or 6 in the next 1 or 2 years. So that is nothing to expect. And you see it still, even going from ICC version 2 to ICC version 4, which was published in 2000, which PDFX standards use ICC version 4. It's more than 10 years old. And even PDFX recommendation recommends PDFX 4, but still with version 2 profiles. So that's why this is something glacial.
X4 allows obviously for
yeah, but not the PDFX pre-flight.
no, because
for good
we
reasons.
found out that some of the devices
Yeah, I know.
cannot handle it that well.
Yeah, I know. I share that recommendations. Yeah, but you see, that is something. I learned the phrase a glacial pace, and that is really a glacial paces. Yeah.